work. My PhD work more generally looked at constructing learning algorithms in financial markets, high-frequency financial markets, when viewed as complex adaptive systems. So of course, this work is sort of joint work with my two advisors, Tim Gebbia and Diane Wilcox. So here today, essentially what we're going to investigate is coming up with a scale-specific state representation for learning agents that are interacting with the system. Since if we do view the financial market as a complex system, then we're going to have different types of behaviors or state representations that are appropriate for the scale at which we're interacting with the system. So there's a fairly rich literature on this paradigm as financial markets as complex systems. I'm not going to go into all the details, but essentially what it entails is you have different classes of agents, each with maybe different effective models that govern their sort of interactions with the system. And these agents are all sort of collectively and simultaneously interacting with the system and affecting essentially their perception of the state. They're sort of creating the state that they perceive as they're going along. So all these conveniences of stationarity and ergodicity and time consistency kind of go out the window when we're trying to construct a useful model when interacting with a system under this paradigm. So we're considering financial markets, in particular high-frequency financial markets. So you can think of essentially constructing an automated trading agent that is essentially receiving an asynchronous stream of events and seeing whether this agent can somehow make sense of the stream of events and make effective decisions. So this broadly fits into this theme of market microstructure, which essentially looks at the true dynamics or the sort of governing dynamics of price formation at this tick scale. So as you have market participants that are submitting orders to this limit order book, you have different types of quotes that are coming in, different types of interactions in terms of trades and absorbing quotes out of that book, and all of these different types of events are happening sort of at microsecond sort of frequency and also occurring asynchronously. So essentially, the broader question in terms of the sort of overall work is, can we find any persistent structure in this sort of asynchronous stream of data such that meaningful learning can take place in this complex system? So essentially what we're going to do is we're going to see whether or not we can look at, if we're interacting with the system at regular calendar time intervals, so let's say regular 5-minute intervals, can we essentially construct a state representation for the temporal evolution of the system at that calendar time scale that is appropriate given this paradigm of complex systems. And the way we're going to essentially do that is to see if we can take a candidate set of, say, calendar time intervals and see whether or not any clustering takes place in terms of calendar time periods. So say 2 different 5-minute periods appear in the same cluster, and we then categorize those as the same states. And if we can in some way detect that we're in that state, then we know essentially what to do. We can learn a policy in terms of an optimal mapping of actions to states. So given this whole this paradigm of complex adaptive systems, the canonical models used in statistical physics to model these systems are these spin glass models. And essentially what we're looking at is a particular type of spin glass model. This is the Q-state Potts model. And essentially what it says is, the analogy is you have a whole bunch of different objects in the system, and each of these objects can take on different magnetizations or spins, each in different directions, in this case, Q possible different directions. And what you can do is you can introduce a sort of ferromagnetic interaction term and control the temperature of the system, and what happens is you have regions of aligned magnetic spins that appear. And what we essentially, the analogy is essentially that regions of aligned spins amongst the objects are essentially the cluster configuration of the system. So aligned objects suggest there's some homogeneity amongst the objects in the system. So this is the canonical Edwards and Anderson Hamiltonian, which describes the sort of the energy state of the cluster configuration, where we have some sort of Jij, which is this short-range, distance-dependent interaction term amongst 2 spins, Si and Sj, and this is an external magnetic field here. So it's quite difficult to actually postulate an actual form or a direct form for this Hamiltonian given a particular problem. But what you can do is you can derive a sort of maximum likelihood approach, which is that of Ghiardo Marsili. And essentially what they say is, instead of trying to postulate a form, what we can say is we can make a statistical ansatz about the sort of generative model for the time series for objects in the system. So we can say for object xi, the time series coming from that object is partially part of that comes from innovations from the cluster it belongs to, and partially from specific sort of innovation specific to the object itself. So it's a bit of a blend of the two. With this coupling factor, or with this sort of weight in terms of the proportion to the cluster is governed by G, and the proportion specific is governed by obviously 1 minus G square root. And if we take this as an hypothesis, then we can essentially, and we assume that the eta SI in terms of the cluster innovations and the epsilon I are the object-specific innovations are Gaussian, we can derive a probability density function given a particular G and S, where S is a candidate structure of the structure or configuration of the object. So we can think of S, if we have, say, 5 objects in a system, then S is essentially a candidate configuration in terms of 1, 1, 2, 3, 4, for example. In that case, the first 2 objects are in the same cluster, and then 2, 3, 4 are singletons, and that would constitute one candidate structure. And we can use that, and we can essentially derive a likelihood function for a candidate structure S, which is this expression here. I didn't really want to go into any of the details, just beyond that we can derive a likelihood expression. The full derivation is in the associated paper. But essentially what this does is that for a candidate configuration, we can sort of evaluate its efficacy in terms of explaining the structure in a given data set. And what we essentially can do then is take that likelihood function as an objective function in an optimization routine. So we chose to use a meta-heuristic optimization routine like a GA. And we can sort of evaluate candidates, a whole bunch of candidates configurations, and then hopefully converge on a best approximation to that configuration which best explains the structure in the system. So there's a separate paper where we essentially came up with a sort of high-speed parallel genetic algorithm implementation. It's not important, just to say that converging the previous investigations which used this approach and used GAs or simulated annealing to try to converge on this best approximation took the order of days and weeks to solve. And using a simple sort of GPU-optimized routine, because we can apply the genetic operators sort of in parallel, we managed to get it down to the order of seconds. So that was just something that was quite neat for future online applications. So the initial sort of investigation of coming up with a sort of market clustering procedure or unsupervised clustering procedure. The other thing that I wanted to mention, what is nice about this procedure is that it is unsupervised, right? In that the number of clusters as well as the configuration emerges from the procedure. We don't have to say there are k clusters or 10 clusters. Find the sort of the configuration that best explains that. Both the number of clusters as well as the configuration emerges from this, based on obviously the full population that we're sort of using to converge in the best approximation. So based on that, the original studies essentially looked at a bunch of stocks in a financial market and looked at how do we cluster stocks based on price as the feature to cluster on. So and we're trying to sort of turn this on its head a bit and trying to cluster time periods instead of stocks itself. So there is precedent for this. So Matteo Marsili did look at applying this procedure at grouping days in a year period based on the closing price performance as the feature to identify temporal states. And essentially what we're doing is we're extending this in some way to intraday temporal periods. So what we're doing is we're taking the sort of top 40 stocks in our exchange. So we've got, I think there's 42 stocks in the exchange. We're looking at these features which we can observe from a top-of-book market data feed, trade price, volume spread, and volume imbalance. And then we're seeing whether we can take all those features and essentially using the features from all 42 stocks as our time series and our time periods as our objects to see whether or not we can group time periods into clusters. And what we did is we did that for 60-minute, 30-minute, 50-minute, and 5-minute, just considering calendar time periods in this case. So what this essentially does is it reduces a significant amount of noisy high-frequency information into a tractable representation from which we can hopefully extract something which is meaningful for intraday learning. So what that gives us, so we essentially take, so in the results which I'll show you just now, we've essentially got, say, a month of data, we've got a month of hour periods, and now we've got this cluster configuration. That's all fine and well, so now we've got the states in that month. But that isn't really useful for online learning. For online learning, we need to know what state are we in now. So we essentially propose this approach, which is a very sort of basic, simple first stab approach, but the concept still holds, we think. Essentially what we do is we take the identified states and we try to extract from each of those states some sort of what we call a state signature vector, which is some sort of signature of market activity which we can measure online. Right? And we associate those state signature vectors with each of the states. And then online, what we do is we measure what that vector is of market attributes, and then we match it essentially to our set of state signature vectors. And then what that does is then we can essentially detect which state that we're in based on this approach. So, so for that, of course, it's maybe not advisable to use. So in the sort of ex-ante grouping of periods. We need to also identify which are the significant states, because i.e. those which are most likely to persist. So there's a bunch of literature by, sorry, how much time do I have? Is it okay? 34 minutes. Okay. So I think I'm just going to get to the pretty pictures, basically, because basically there's literature that suggests that if your system that you're investigating is a complex system, then any stable inferences from the model can only take place if the system is at or near criticality. And based on that argument, what we essentially do is we use a best power law fit to our cluster sizes to extract the persistent states. But all of those are just details. Let's just get to the pictures. So essentially what this is these 60-minute clusters, right? So every single node in this picture is a 60-minute period in one month, okay? And essentially the clusters are represented by the node connectedness, right? So the first thing that we notice is that there are clusters, which is comforting. So they're not all singletons. The second thing is the nodes are colored by their time period during the day. So green is the morning, yellow is lunch, red is the afternoon, because there's these sort of stylized facts in financial markets that they have these sort of U-shaped sort of patterns of behavior, so we wanted to investigate whether that is corroborated with the clustering. So what we do see is that there are, well, firstly, they're definite clusters, but there are also these definite sort of morning and afternoon clusters that seem to appear. So there's, in the South African market, we are affected by the sort of opening of the US market and the opening of the UK market. So this cluster, in fact, coincides with the opening of the UK market because they're dual-listed stocks on both exchanges and the UK investors get involved. And this coincides with the US market open, which is quite interesting. And then essentially what we did is to extract the significant clusters from here. We fit this sort of power law. I'm not going to go into the details. Needless to say that there is, using this particular method, this maximum likelihood method of Clauset and Shalizi, anything above with a p-value above 0.1 is significant, so that's good. But essentially what we then using is all the clusters with a size or a number greater than 13, so a number of nodes greater than 13, those are going to be our significant clusters. And then what we're going to do is we're going to extract these state signature vectors, which is essentially the sort of average pattern of feature performance across all the periods in a cluster across all the stocks. So very crude, but just sort of one candidate approach. So these are essentially our 6 candidate states. So what they're saying is that out of all of these, 6 of these satisfy the power law according to that approach. And these are the 6 signatures of activity. And then if we use those 6 signatures to try to extract the states, then this is essentially what we get for the same period. So using this approach, even this crude approach, we're able to kind of recover at least some of the significant exogenous-driven clusters that appeared in the temporal state, but bearing in mind that these can effectively be measured online. So we essentially repeated the analysis. This is for 30-minute clusters, and we did it for 15 and for 5, and just noting that in every case, there was no definite sort of hierarchy of, so 5-minute clusters make up 15-minute clusters, or 15 minutes make up 60-minute clusters. So there's definitely some different behavior that happens, and if I show you, just want to go to the 5-minute clusters, for example, very different behavior, a lot more singletons, and a lot of the periods that were together before have now split up into their own different clusters. So there's definitely different signatures of activity that exist at the different calendar timescales. This was just a bit of a stability study to see whether or not these, because we're measuring these distances of these state signature vectors to the set, we wanted to see whether or not those distances sort of persist out of sample, or whether or not it's just, so this was just to essentially see whether or not we can in fact use state signature vectors extracted from a particular month, and whether or not those last long enough out of sample. But I think the details aren't important there. So yeah, so this is essentially just a scheme for unsupervised determination of intraday financial market states, and then using those to essentially extract signatures of market activity, which we can measure online, so that we can detect which state we're in online. The important thing here is that the state representation is scale specific. So in further work, we essentially extended this to event time. So we've looked at calendar time here, so the clock is ticking according to, say, 5-minute, 10-minute periods. But there's this notion in financial markets anyway of machine time or event time, where the clock ticks according to, say, the number of traded volumes of a stock. And that governs the sort of clock ticking for the entire market. So if you repeat the analysis, essentially in event time, you get very different clustering behavior, but all of the indications of a complex system are there. So all this, so the power laws are all significant, and the efficacy of the model is better in event time. So just to mention that in subsequent studies, I applied these in a learning agent, which essentially uses this as the sort of public state attribute, and it outperforms other models. So just to say that. That's it. So,
okay.
Yeah.
Okay, thank you.
Yeah.
One quick